Thank you, hosts, ladies and gentlemen, for inviting me today. I'm going to share some innovations in vision rejuvenation. This is a departure from today's current paradigm in vision corrective procedures to vision rejuvenation using a biomechanical model. So Dr. Goes asked for a new paradigm, and I'm pleased that you're excited to offer you at least one of those such paradigms today. So I'd like to thank my co-authors who in some way contributed to this content, and also to disclose I am the founder of Ace Vision Group. So we got a lot of accommodation introduction today, but I just want to refocus you a little bit, if I can, that we need to remember that accommodation is in a dynamic way, is a range of motion, a dynamic range of motion of the lens, a physical dynamic range of motion when we're dealing in a natural system. And so that's what we expected to do, and that's the problem we have in looking at restoring rather than correcting. And we know that lens stiffness is a problem in this. And also, Strength et al. And others have stated that the ciliary muscles are contractile, and there's a problem in disaccommodation, and there's a problem in loss of ability to either disaccommodate due to increase in lens thickness or hardness, and or inward movement of the ciliary ring, or both. So this is well published, and we know this. We have a whole industry around lens stiffness and hardening. But we also need to pay attention to a couple other anatomy. So another part is that increased scleral rigidity, which has been largely ignored until more recently, and hopefully it'll get some more attention. So we have to understand that this is a complex force mechanism, and yes, while we have resistance in the lens stiffness, we also have increased scleral rigidity through time, and we need to be worried about that for some reasons we're going to go over. So I asked the question, could age-related scleral rigidity cause a biomechanical dysfunction internally? Well, we know that in aging, collagen changes. We have thickness and rigidity. We have shear strain, tissue stress. We actually have architectural change. We have lens hardening, ciliary muscle hypertrophy in parts of the muscle, anatomy crowding, and increased ocular hypertension. So in one of my manuscripts, which was my PhD manuscript, I wrote a model to address these issues to see if we could impact visual function and other function possibly by looking at these imbalances. So let's just talk about structure equals function. 5/6 of the eye is covered by sclera, and it begins to harden starting at the age of 40 and becomes virtually inelastic by the age of 6th to 7th decade of life. So we really can't ignore this white part of the eye. I sort of did a little simulation here that 90% of the intraocular function of the visual system is beneath the scleral outer coat. And, you know, scleral rigidity plus lens stiffness has a negative impact on the ciliary muscle forces. And these are models that we're building now as well. A lot doesn't exist, so we're going to go over some of those ideas today and concepts that this is built on. So how does ocular rigidity and loss of accommodation impact physiological health of the eye? Well, to just be simple, force equals mass times acceleration. I'm going to go through a little bit of Newton's principles, and John will appreciate that, I think, hopefully. But viscoelastic modulus, that's the ability of the globe to depress with force and return to shape. It's about like racquetball. I don't know if Europeans play racquetball, but it's almost like a tennis ball. You can deform it, and it's very pliable and movable by forces, whereas the viscoelasticity as a 50-year-old is like a baseball. It's very rigid. A lot of force is lost pressing against that structure. So this is actually an adaptation article. I lost the reference here, but I will have it in my references, by Ross Ethier, who studied ocular rigidity as it relates to accommodation and eye health. So the contraction of the ciliary muscle is not only for dynamic function of the visual function, but also for the eye organ. When the eye accommodates, the ciliary muscle contracts, it opens the valve by the way of the scleral spur, it circulates all the fluids and the nutrients of the eye. Ocular rigidity and the loss of accommodation therefore impacts more than just vision function. It's basically the heart of the eye organ. So it is an important function of the eye that we can't ignore, that plays a vital role in that organ of sight. So we know that loss of accommodation is correlated with age. We've seen a lot of publication of that. But we also have some pretty interesting and further growing articles that show that ocular rigidity is a powerful constant for age as well. And the peak onset of the rigidity of the oculus, the sclera, happens just about the same time as the peak onset of the most drastic loss of accommodation. Recently, we also have seen ocular rigidity in the research been correlated with decreased ocular pulsatile blood flow. That's not really surprising considering the vast plexus that's right underneath of the oculus or the sclera. Now, the sclera is not innervated nor is it vascularized, but all those precious vessels do pass through the sclera. Ocular rigidity has also been correlated with certain forms of glaucoma, and these are new studies being done more and more. Ocular rigidity also has been recently correlated with the pathogenesis of AMD. Now, ocular rigidity, due to its health correlations, may contribute to a formation of a cataract. It's been sort of speculated upon. It hasn't been specifically proven, but isn't that interesting? And it should become a further interesting topic that we should be looking at in the future. So the visiodynamic theory was published in 2003, and what it is a biomechanical application for the aging oculus. And there's some terminology that's used in biomechanics that's not really common, so I'm going to take a little time to go through those. And what is visiodynamics? So the goal was to understand the acting faculty of seeing, visio, and the phase of mechanics, which deals with motions of materials and bodies taking place under specific conditions. And as we know, aging is a specific condition. We can definitely identify with specific physiological things that are happening to us and demonstrate function loss with aging. So instead of looking at, again, vision correction, the goal was to say, gee, how can we understand this and how can we restore that? So when we apply this to presbyopia, age-related consequences on connective tissue, of which the eye is 95% made of, as they occur throughout the body, have significant irreversible impact on the body, most distinctly scleral compression or sclerosis of the sclera that happens with age. And these things have been demonstrated to have impact on biomechanical efficiency of what I've termed the oculociliary joint. That's the connection of the sclera through the tendons of the scleral spur to the zonules, to the capsule that was described this morning by Dr. Beauvais, and to the lens, which actually moves something with a particular force in a direction, and that's the definition of the joint. So that whole complex is what I mean by that. Ocular biotransport, which we just saw in the last paper, that the heart of the organ is that complex, that only moving dynamic part circulates everything in the eye, down to metabolic efficiency and even extracellular matrix efficiency. So let's just look at what a normal cascade of aging is, and this big scleral coat that you see is impacting all those lovely structures that we know provide us all these visual capabilities. This is a typical, not just direct to the eye, but in every collagenous tissue in the body as it ages goes through this cascade, and it's a vicious circle of compression, physiological stress, hypoxia. Your architecture changes, you have a load of the coat, your interocular pressures and the homeostatic mechanisms sort to react to that, and you have stress. So how can we understand ocular kinesiology, that's the movement function of this whole system, and restoring that? Well, we first have to understand what is the problem we're trying to solve. The problem we were trying to solve was the accommodative neuromuscular system is the primary dynamic moving mechanism of the entire eye organ. When it stops working efficiently, so does all dynamic physiological function of the eye organ, including visual function. So how do we look at this? To restore that, we have at least 3 requirements. We need to balance the dual optical system, and in a natural system, you still have to deal with the cornea and any problems in those optics that are, taking away from your accommodative power. You have to facilitate the accommodation system to diffract and do forces in the direction that you want them. and the direction that you want them are obviously we want to have that lens center repeatedly moving so we can have better vision in all ranges, and we want to alleviate this scleral rigidity factor. So, what are the solutions? We have exchanged power in the cornea and the lens, and we've seen a lot of those solutions today. We saw a new one, which was a pharmacology solution. We're finally getting some knowledge on how to restore natural function of accommodation, and you will agree with me that the use of the principles of optics are very useful to solve these optical problems. Now, we're going to need to explore some principles of motion to solve the complexity of restoring true accommodation. So, albeit a little bit dry, we're going to have to go through some basics. Kinematics, which is the science of movement, is based on Newton. They're just 3 simple Newtonian principles that we need to just revisit if we're going to understand restoring accommodative movement and function. So before I show you the exciting other animations, I think we're just going to go through a few laws. So the first law, an object remains at rest until it's acted on by an unbalanced force, right? Law of inertia. So what does this mean? Where we're looking at this whole system, this means that there's a natural tendency for objects to keep doing what they're doing. All objects resist changes in their state of motion, and in the absence of an unbalanced force, it will remain in state of motion. So, if the sclera is pliable, if the lens is pliable, all the forces on the lens are going to continue to do what they're supposed to do. What's the second law of motion? Acceleration is produced when a force acts on a mass. The greater the mass, the greater the amount of force needed. And everybody kind of knows that. What that means is that more mass means more force needed to accelerate. So basically, when the sclera and the lens become more rigid, it increases the resistance to these resultant forces to move the lens in the directions that we desire it to move in order to have basically resistive-free visual function and range of motion. What's the third law? For every action, there's an equal and opposite reaction. So, basically, the more sclerotic the sclera, the more dense the lens, the increased ocular rigidity in total will increase slurring muscle force required to move the lens. The sclera and the lens resist with equal forces and movement, and this creates a biomechanical imbalance and dysfunction. So, we saw a lot of theories that we went through today. I'm going to offer you one modern accommodation theory that's courtesy of Dr. Dan Goldberg. This theory seems to complement our model, and we're doing some work with Dr. Goldberg on UBM and other things you'll see today to see if we can try to map some of these forces that we were just talking about. So I'm going to show this video. Hopefully you
Theory of reciprocal zonular action. Dr. Daniel Goldberg now proposes his theory of reciprocal zonular action and formulates a new consolidated theory of accommodation as follows. The engine of accommodation is the contraction of the ciliary body mediated by the distribution of forces via all elements of the zonular apparatus. The resultant changes in refraction are due to the increased thickness of the lens and the increased curvature of the anterior and posterior capsule.
So that was an abbreviated version, but I just wanted to demonstrate by animation some of the
ciliary body contraction resulting in anterior and centripetal movement of the ciliary body, decrease in diameter of the lens equator, and increase in the lens thickness. The anterior lens capsule moves forward and the posterior lens capsule moves backwards.
So again, this is yet another theory. We have a lot of work to do in accommodation, but I think the most important part is to identify with as we're looking for range of motion in that lens. Exactly the anatomy that's connected to that remains to be seen. The laser edge procedure, which will be further revealed by Dr. Rohn later, was designed to restore dynamic accommodation, helps to increase that range of motion. And the goal is to increase pliability in the sclera, increase net forces on the ciliary muscle in the lens, and facilitate accommodation. So I'm going to show you a brief animation of what that procedure consists of, and Dr. Rohn is going to show you some live surgery later. So here you see a marker. Today it's in 4 quadrants to avoid the vessels. Not on the visual axis, Today it's also done by handheld probe. And specifically done over 3 physiological zones of importance, as well as burn, the mid-muscle belly, and the origin. So the goal is to basically decompress that muscle and allow it to have as much pliability and movement as possible towards the lens. And again, theoretically, the biomechanical effect of this would be that we have some mobility, more increased mobility in that area, and some increased centripetal force in the lens to allow the patient to have more range of motion. So, bottom line is, if we can increase the ciliary forces by decreasing the resistive forces, we could get more power to the lens. And again, going back to Newtonian principles, a muscle can basically work more efficiently when working against something more pliable than something more rigid. And we believe that laser rays could improve scleral viscoelasticity, improving unresisted ciliary muscles forces on the lens. So, in conclusion of this portion, ocular rigidity has been correlated to important pathophysiology of the eye, and new paradigms for understanding these corrections are emerging. The laser rays procedure in preliminary study does show the ability to improve clinically significant dynamic accommodation function. Does it have other potential health benefits? Possibly. But without putting an implant in the eye and without touching the cornea, we are getting some substantial clinical improvement of that accommodation function and range of motion. So we have lots of studies to do to improve knowledge and to expand treatment paradigms. We have a lot to learn about measuring accommodation in vivo. We're starting to now just look for opportunities to establish diagnostics and models to really put the proof in the pudding with our results instead of just having clinical visual acuity and questionnaires. So without that, we say because accommodation is extremely complex, the job of restoring it is going to be a long and difficult path with lots of challenges ahead. Despite this, we must ride the storm. And I think this little next video will really describe where we all are at in after 100 years of Helmholtz, we're still trying to figure this out. So here's a little animation that relates with my feeling on this topic and maybe yours.
What a filthy job. Could be worse. How? Could be raining.
So just when you think we have it all figured out, we always come up with another problem in presbyopian accommodation, and it's just a Pandora's box. And what the exciting news is that hopefully we can have some new paradigms to look at the real problem of presbyopia in conjunction with all these great vision correction things that we already have evolving by the speed of light. So thank you very much for your attention.